Today we're gonna walk through a code kata that's on Codewars. It's the one where you get to write a function to decide if an integer number is prime or not. We're going to do this in R. So these are the instructions. We are supposed to write the function called isPrime, and the requirement is that it should take an integer argument, return a logical value true or false, depending on if the integer is a prime. The prime being defined as a natural number greater than 1 that has no positive divisors other than 1 in itself. Very important to read the requirements. You can assume that you will be giving an integer input, so no need to guard against that. You can not assume that the integer will be only positive, so it could be negative, and in this case we should probably return false, I suppose, according to this example here. And a very important note on performance. So I know that there are very good algorithms like I think the Eratosthenes sieve or something like that. We are not going to implement that unless we really hit a bottleneck. So, but they also say that the most trivial solution might time out. So we are going to go for a suboptimal solution, but one where we will avoid the most naive solution anyway. Okay, cool. So we go to R, we go R script. So the way I like to do those kinds of things, we're gonna be very deliberate in using TDD for this, so test-driven development, and it's gonna sound really pedantic, but there's a purpose. So I'm using test.dat, by the way, as a library for doing TDD. So the first thing, we are going to just load it. Test that. We make sure that it works. Okay, fine. So in test.dat, the way you write a unit test, you test that, and you write first the description. In this case, I'll just use a generic description for everything. Primality function works, or something like that, and then you specify the body of the code, and we're gonna just write all the unit tests directly here. So the first thing I always like to do, I like to write to make sure. Well, I like to write something that's going to obviously fail, just to make sure that the unit tests are specified correctly. So in this case, I'm going to go maybe expect. I think they have something called expect. Okay, we have expect false, and we have expect. I suppose we have expect true somewhere. So expect true. Actually, false is prime. Let's do the edge cases first. So is prime 0. 0 is not supposed to be a prime number. Now this will probably fail, and that's fine because I want to make sure that this gets executed. Is prime is not even defined, so I want to make sure that this works. So I'm gonna hit I think it's Command Shift S. This sources the whole thing here, and as you can see, it fails. That's good, and it fails because there's no function called isPrime. This is exactly what I wanted. So I'm gonna keep the library import at the top of the file. I'll just write the smallest amount of code that will still work. You know, actually, I should have not even specified an argument here. So isPrime function that doesn't do anything, something like that, and now it fails, but for a different reason. It fails because the return value of the function is null, whereas we should expect a false. Okay, now I think that's a good time for introducing arguments to the function. So I'm gonna go n and 0 here. It should still fail for the same reason. You know what? I'm gonna there's a place somewhere where, yeah, I'm gonna remove the breaking code thing, just the message only. So now when it fails, I should just get the. I need to restart. Or I think. So now when I run it, it's gonna fail. Okay, so now we introduce an argument here and here, and this should still fail because it returns a null. So what's the smallest amount of code I can write to get away with this? I'm going to just return false. So when I do this and I rerun the whole thing, it says test passed. Okay. Now this may feel like cheating, but this is actually normal. This is what you do when you do test-driven development. You write the smallest amount of code that still works, and once the tests pass, you start thinking about refactoring. In this case, I don't see anything else that I could do. So I'm gonna start implementing the rest of the requirements. The other one, I'm gonna put them before the one about 0, because it kind of makes sense. So is prime -1. So negative numbers should also return false. This passes because that's just the default answer here. I'm gonna do the same thing for 1 and 2 and 3. Sorry, no, not 2 and 3. So these numbers should still pass, and this is correct. Okay. Now let's do something more interesting. 3 should be, sorry, 2 should be prime. So this will fail. Okay. So what's the easiest way we can get away with this? Well, you're gonna be very shocked by this, but if n equals 2, return true. Otherwise, no, sorry, I don't wanna save this. Otherwise, return false, and this passes the test. Okay. I still don't see any reason to refactor this, to be honest. So we'll just continue. Let's write another test for 3. And now we need to stop being silly. We need to do something real now. Okay. So before we do anything here, so I'm gonna comment out this guy for now. There's one thing I wanna do. I wanna make it clear in code that any number smaller than 2 cannot be a prime. Well, so by the way, first of all, let's check. This still passes. Okay. So if n less than 2, we return false. This should still pass. Okay, fine. If it's equal to 2, we return true. So now what we could do is to say, if let's say if it's an even number, it's not a prime, otherwise it is. So the way we do this in R, we go if n, I think it's %%. If this is the case, then return false, otherwise we return true. Good. Okay, so far. Oh, I didn't even test it, so let's see. Let's check that this tests. Okay, it passes. Right, now you can see where this is going. So I know how to guide this now, because I know that this will I just happen to know that this will work for 5 and 7, but not for 9. So let's write a test for 9. So 9 should not be a prime number, and it fails, of course. Okay. So now I think we need to write something that's less silly. And the most naive test is to just loop through all the numbers up to n and see if they divide the number. So I'm gonna keep the test for parity around just because I don't see a reason to remove it. So for I'm not gonna loop on I. I really don't like people who call things I, but I'm not gonna be better. I'm gonna call it D. For D in what is it? Well, 3 I suppose. 3 to n. If n mod D equal 0, return false. Oh, should be up to n minus 1, of course. If not, return true. So this, okay, this doesn't work. Is prime 3 is not true. Why? Because, oh, I see. Yeah, for 3, yeah, 3 divides 3, of course. Let's start this loop from 2, which means we don't need this conditional here. Yes, this passes. Okay, now at this point we have a working solution, and this, I mean, this code is correct, but it's slow. And actually, if you pass this to Codewars, they will tell you that this will time out. So the most obvious thing you could do is not loop until n minus 1. You could loop until square root of n. So let's try that. So we have some, it works. There's no immediate reason to refactor it. We could just do this optimization now. So now this is going to be interesting, because the naive thing to do would be to go square root of n. And this will, okay, this will still pass. I did not entirely expect that. That's interesting. Let's see if this works for all the numbers until 9. So expect this should be false for 4. Okay, fine. It should be expect true for 5. Okay. It should of course be false for 6. All right. Okay. So it works 1, 2, 3, 4, 5, 6, 7, 8, 9. And yeah, if it works until 9, I think there's no reason to believe that this will not work. So this works, and this is much faster because we only search up to square root of n. The reason why I was a bit surprised is that square root of n for numbers smaller than 9 is going to be, well, less than 3, so 2 point something, which means that, so in R, if you specify a sequence like 2 to 2.1, that's just one number, okay, which is probably okay in this case. Okay, now that's fine. The final piece of optimization I want to make here is I want to avoid testing for even numbers here, because if the number is divisible by 2 anyway, we don't need to test. So we could test for only the odd numbers in this sequence here. So the way we do this is, well, first we need to test if the number is even. In this case it's false. This still passes. Okay, and now, so the way to do a sequence with a step different than 1 is to use the function sec for sequence. For example, sequence 2, 9 by steps of 2, this will generate the, well, all the even numbers between 2 and 9. So we don't want to start at 2 now. We want to start from 3. Actually, you know what? Let's be brazen here. So sequence from 3 to square root of n in steps of 2. We could even name the arguments. I think that would look nice. From 3 to square root of n by equals 2. This will, I would be surprised if this worked. Right, okay. So this doesn't work. For which reason, for which value does it not work? Does it say that? Oh, is prime of 3 doesn't work. And it doesn't work because sequence, well, to understand what's going on, a sequence of 3 to a square root of 3 by 2 says the wrong sign in the by argument. Is that what the error said? Yes, wrong sign in by argument. See, I didn't even read the error message here. It should have told me this. So it's the by argument has the wrong sign because square root of 3 is less than 3. So if there was no by argument, it would, you know, it generates a sequence that goes backwards. And this is going to be a problem for any number whose square root is less than 3. And there's no, I don't see any way to solve this elegantly in R actually. I mean, in the sequences in Python work a little bit more like what one would expect in those cases. In R, there's no easy way for me to specify a step size of 2, but only when the 2 argument is greater than from. So the way I'm gonna get out of this one, I think the easiest way is to include a specific test for numbers for which the square root of n is less than 3. So all the numbers from basically from 3 to 9, I'm going to test them explicitly. So that means that if n is in, no sorry, it's percent in, so wait, we already did test for, so all the prime numbers between 2 and 9, this is 3, 5, 7, yeah, that's it. Return true. And any other number is even, so it will be returned. You know what? This should work actually. Okay, it does. It does, and we can even do a little bit of cleanup. Like we could include a 2 in here. So I'm plonk this here. Actually, this also should work. Okay. So if it's less than 2, we return false by definition of a prime. If it's 2, 3, 5, 7, we return true. If it is even, we return false. And in every other case, we test from all the odd numbers up to square root of n in steps of 2. If the number divides it, we return false. Otherwise, we return true. And that's probably the best we can do here.